Hello everyone, I'm Wang, PhD candidate from Shanghai Jiao Tong University. I'm very glad and excited to share our latest research. We developed a numerical model called Multiple Thermally Thick Particle Model, abbreviated as MTTP model. This model is suitable to simulate the fixed bed thermochemical conversion of solid fuel mixtures. And in this presentation, the scenario of fixed bed co-gasification will be introduced. We know in recent years, the interest in utilizing various types of solid fuels is fast growing, including agricultural and forestry residues, sewage sludge, and plastic wastes in municipal solid waste. These solid fuels are generally decentralized and are preferred to be locally utilized. Therefore, fixed bed co-gasification technology is very suitable in these scenarios for its low capital cost and smaller size of the reactors. However, in many circumstances, these fuels are not directly applicable for thermochemical conversion. Sometimes the heating values are too low owing to the moisture content, such as sewage sludge or raw woody biomass. And sometimes the ash content is too high, such as for straw, causing ash agglomeration. To efficiently utilize these unideal fuels, many researchers have explored the co-gasification technology. The basic idea is to properly match different fuels to reach an acceptable average heating value or ash content. Sometimes synergetic effects may also occur, for instance, generating more hydrogen. However, mixing different solid fuels in the conversion system can be a very challenging task, especially for quantitative evaluation of reactor configurations or optimization of working conditions. Numerical modeling is a very powerful tool for analyzing the gasification processes with low cost and low accuracy, comparing with conducting large number of experiments. In general, there are three approaches to construct a numerical model for fixed bed gasification system. And among these approaches, CFD-based models are most powerful. Both the complicated heat and mass transfer in the system and the chemical reactions, both in solid and gas phases, can be considered. For fixed bed gasification, the most common modeling method is the classic Eulerian approach, which regards the multi-phase system as a porous medium, so that the conservation equations of different phases will share the same general form. This method is very efficient, and the simplification is quite acceptable since the motions of solid particles in fixed bed system are not very significant. However, for fixed bed co-gasification process, there are two challenges for constructing the numerical models. First, for the solid residues we just mentioned, the fuel particles are generally centimeter-sized or even larger, which are classified as thermally thick particle. In this case, the temperature gradient inside the fuel particles is not negligible. We can no longer accept the assumption that the solid phase is homogeneous in each computational cell. Secondly, when using fuels with different characteristics, such as different moisture content or different particle sizes, the conversion process will be asynchronous. For instance, when the wet fuel is still preheating and drying, the drier fuel particles may have already been ignited, and different fuel particles will interact with each other in this process, and this must be reflected by the numerical model. In our MTTP model, we try to solve these two problems by extending the classic Eulerian approach. For classic Eulerian approach, the solid phase can be regarded as a homogeneous phase in each computational cell. And now let's consider when mixing two different fuels. The solid phase will firstly be divided into two subphase groups representing two fuels, and their volumetric ratio will be determined by the initial condition, and that can be changed in the following conversion processes. Each subphase group is composed of 4 subphases, representing the wet fuel, the dry fuel, char, and ash layer of each particle. Initially, there are almost only wet fuel layer for each fuel, and other layers are assigned with a negligible initial value. When exposed to high temperature, drying process will firstly take place, and the wet layer will be converted to dry layer. That means the volumetric ratio of the wet subphase will decrease. The moisture will be released to the gas phase, and the rest of solid components will be handed to the dry subphase. This is identical for the conversion of other subphases. More importantly, different solid fuels can behave differently in this model. They can have their own initial composition, pyrolysis kinetics, and particle sizes. They can keep their own characteristics. Meantime, they can interact with each other by convective heat transfer with the gas phase or radiative heat transfer with each other. In MTTP model, different fuels could convert based on their own composition and properties, and this is fundamentally achieved by solving the mass and energy conservation equations. Since these equations share the same general form, the most important task is the formulation of source terms. With proper source terms, the expansion and shrinkage of each subphase could be described, and the temperatures of each subphase from exterior to the inside of the fuel particle can be calculated. Here, I'll briefly introduce the formulation of the source terms for energy conservation of solid subphases. In MTTP model, the energy source term includes 5 subterms. Here, S reaction is the heat source or heat sink caused by the reaction in the corresponding layer, such as the latent heat for drying or the heat of char oxidation. S conduction describes the conductive heat transfer from the adjacent layers following the Fourier's law. S blowing stands for the intraparticle convective heat transfer caused by the outflow of moisture and volatile. This is very important for solid fuels with high moisture and volatile content. And S evolution refers to the net enthalpy change caused by mass exchange. For instance, the dry layer will receive mass from wet layer, and it may also give mass to char layer. Finally, S environment includes all the convective and the radiative heat transfer with the environment, with gas phase, and with other fuel particles. And this term is only activated for the outmost layer of the fuel particle. Validation of our MTTP model for co-gasification process was performed based on the experimental work by Boy and Hank. They performed co-gasification experiments in the commercial scale downdraft gasifier using MSW pellet and switchgrass as fuels. The MSW pellet was large in particle size, mainly in cylindrical shape around 2 centimeters long. Meanwhile, the switchgrass was chopped into smaller size, around 5 millimeters. Considering the large difference in particle sizes of these two fuels, the conversion process inside the furnace will differ from using only one single fuel. The authors provided the temperature distribution and the gas compositions from experiments of different mixing ratios. The measured values are in quite good agreement with our predicted results. And the numerical model also reproduced the general trend of temperature and the gas composition when changing mixing ratios. With the increase of MSW pellet in the conversion system, the maximum and average gasification temperature gradually dropped as it behaves in experiments. The modeling results could provide a complete temperature profile for the whole gasifier. This is very important for evaluating the performance and optimization of the gasifier. For simplification, the numerical modeling in our work was performed in one-dimensional, but higher dimensions are also feasible just to take the radial inhomogeneity into consideration, such as the heat loss from the wall or distribution of oxygen introduced from side of the wall. Not only could the numerical model show the general trend and performances, we can also analyze the detailed conversion behaviors inside the furnace. Here, we show two interesting profiles. On the left hand is the particle conversion ratio. Figure 8 clearly indicates that smaller particles will start conversion earlier than the large fuel particle. This is very crucial when mixing fuels with different properties we call asynchronous particle conversion. And figure B on the left also indicates that increasing the mixing ratio of large particles can influence the behavior of smaller particles. That implies different particles can interact with each other and influence their conversion behaviors. The two figures on the right side give more details inside the fuel particle. For smaller fuel particles, the duration of drying process is short, and the temperature difference between inside and outside of the fuel particle is not very significant. But on the contrary, the duration of drying process is much longer for large particle. The temperature difference between the center and outside of the particle is very large until the end of drying. And we would also like to mention that recently we extended the MTTP model, not only for co-gasification, but also for co-combustion process in fixed bed. The gasification experiments I introduced just now mainly focused on different particle sizes. And for co-combustion process, we performed experiments in the bench scale reactor. And we paid attention to the difference of moisture content in this experiment. We used the wood sphere and the fresh potato sphere as representatives of low moisture and high moisture fuels. The MTTP model, it also successfully predicted the co-combustion of thermally thick solid fuels with diverse fuel compositions, and more importantly, the numerical results revealed the in-bed distribution of different conversion stages, the overlapping of different conversion stages, including drying, devolatilization, and char reaction. It is clearly depicted by the modern results that the behavior of these stages is very different from the conventional theory of fixed bed combustion. We often think that the solid fuel will firstly dry up and then go through other conversion stages. But when using large fuel particles with high moisture content, it can be seen that the drying process can accompany the whole conversion process. This is a very crucial characteristic, and it can be modeled by the MTTP model. That's all for my presentation. Thanks for your patience and attention. If you have any questions, please feel free to raise them, and I'm very glad to answer. Thank you very much.
Thank you, Lingjang. Any question from the audience side? Okay. So I have one question, Lingjang. So you mentioned something about contraction and expansion, considering contraction and expansion for the particles. Let's say how you are taking care of that. Do you are you solving any, let's say, mechanics equation for that or anything like that?
When we deal with the shrinkage or the expansion of each phases, it's mainly achieved through the mass conservation equations. That means when one subphase, like for example, when the dry layer of a fuel particle is being dried and moisture is evaporated, and then we take that, we think that the wet layer will shrink, the moisture will be released to the gas phase, and there are other mass, there are dry fuels, they will be transferred to the dry layer. Therefore, by exchanging this mass through the source terms of the conservation equations, and the wet layer will shrink and the dry layer will expand. And through this relationship, we can achieve the shrinkage and expansion of each subfaces. And if we have some accurate values of the densities of each layers, the shrinkage and expansion of each subface will be more accurate.
Thank you.
Thank you for your question.